Hi, good afternoon. I am very grateful to have been invited here by Jasper. And after my publication on the Geophysical Journal International, and I want to acknowledge my co-authors for that paper. Um, and I'm going to be talking of one part of my PhD, so the marine CSEM synthetic study to assess detection of a CO2 escape or leak and saturation changes within the seal in the context of a submarine chimney connected to a CO2 storage reservoir. I'm not going to talk too much about this because we have been repeating why do we do carbon capture and storage and the importance on the energy transition. One point that is important is, well, my study is offshore, so it analyzes the CCS offshore. And we have talked a little bit about it yesterday, about why is it so important to consider CCS offshore. And one of the reasons is, well, the amount of information, because there are plenty of oil and gas activities that have been carried out already offshore worldwide, but also because there is a lot of existing infrastructure, and that could be considered in the future for cost reduction in terms of operations. And we have talked about how this could be done and in which cases it's not possible. So why are we monitoring? We also had a lot of discussion about this and the importance of monitoring, mitigation, and verification strategies. That they are, in my opinion, critical to ensure the safe and permanent CO2 storage. There are many other reasons why we want to do this, but one of the things is to make sure that the CO2 stays where we have been permitted to inject it, and if we detect a leak, so we can do something about it early enough. So there are several monitoring techniques. We have seen some of them in this workshop. So one that is widely used is time-lapse seismic or 4D seismic. And one example where this has been used extensively, and maybe we could discuss if it's too much or enough, or it was just because it's a proof of concept, was in Sleipner. So you can see the figure on the right-hand side, where you can see the seismic sections before injection in 1994. Injection started in 1996, and we can see, well, the value of this in terms of seeing where the CO2 is going, both in the layers within the reservoir and how this through time also expands through the laterally. So this shows, well, why do we do um, 4D seismic? And then you can see also the amplitude maps at the bottom, where you can see also through time how the plume is expanding as you inject. And we could see that these responses are not homogeneous. So that we have a lot of heterogeneities in the reservoir. And this is one of the reasons we monitor. My talk is not about seismic or 4D seismic, but more about what is the additional value of CSEM into monitoring. And I'm going to be presented at synthetic CSEM study. So one of the reasons why we think a multi-physics approach or potentially using electric resistivity together with seismic is, well, I'm showing here a similar graph on the left to what has been shown before in the previous presentation. This is for specifically a patchy model. So the gas distribution is patchy within the seal, and that's realistic on what you will expect potentially on the seal, and it's a little bit of an exaggerated response in the velocities, but to kind of depict the importance of bringing electrical resistivities. You can see in the left-hand side, you have P wave velocities, and you can see that what you will expect is that there will be a rapid drop on P wave velocities as saturation increases, and that P wave velocities will be less sensitive as this happens. While the electric resistivity will do completely the opposite. It will be um, obviously a range where electric resistivity will be less sensitive to the saturations, that after a specific threshold, their saturations will increase very rapidly. So this will just is to just simply depict that having both methods will help you and quantify how much CO2 is in there, will be leaking through the seal. So first of all, what is marine CSEM? So the method is based on um, throwing a transmitter, an electric dipole in this case, through the seabed, very, very close to the seabed. And in this case, I use EM receivers on the seabed. So as the electromagnetic field propagates to the subsurface, your electric receivers would read um, the electromagnetic field. In this case, I have used only electric dipoles, so I'm just measuring the electric field, the vertical and the horizontal component. And then what happens with CO2 or any other fluid, as you encounter a that will be a CO2 plume or a methane saturated reservoir, for example, the electric field will be elevated and this will be measured at the receiver. So this provides an EM target when you have a CO2 plume. So my study, so I have actually for my study, I also have a real CSEM data set, but it was acquired on an area of the North Sea called the Scanner Pockmark. So in the UK, sort of the North Sea, close to Sleipner. Um, there we acquire a lot of data for the STEM CCS project. And I did model for this study using the same geometry of the acquisition. I use the scanning pockmark that is an active gas vent that is connected to a 1,500-meter wide chimney. That will be a very good analog for a bridge to the seal. So I have used all the geological parameters and properties for the geology on the scanner pockmark. So you can see on the right-hand side a seismic section. So this is the pockmark, this seismic chimney, and the sediments on the top are mainly clay sediments. And I have used the Sleipner CCS induction size as an analog for the reservoir and the top seal. So very briefly to show you how I created the model. This is a very busy slide, so bear with me. So I use seismic data to kind of build on the 2D model that I used to create my synthetic CSEM data. So I use the thicknesses from the seismic, the geometry of the chimney from the seismic, and literature values for the porosity and the different properties to be able to model resistivity. And I use for the Sleipner field existing open source well-log data and published information for the thicknesses and the porosities. And then what I did is I used two models, one for the reservoir, the Archie's resistivity law that relates the resistivity with the saturation to build different scenarios where I saturated only the chimney and left the overburden um, like saturated only with brine. And then for the reservoir, I used properties of the zero formation from Sleipner and just the Archie's law. For the seal, I used the modified Archie's equation, the Waxman-Smith, that considers the level of or the amount of clay in the formation that I got from the well logs. So then you practically build a 2D model of the subsurface, a resistivity model. You get synthetic vertical and horizontal electric field data. You add Gaussian noise, and then using a quadrilateral mesh, I did 2.5D inversions using a half space model. And what you get is something like what you see there on the right. So I built different models. So one of the things I did is I saturated first the chimney with 20% CO2 and with 50% CO2. So both models were detectable for this size of chimney. And so these are published in my paper. And I also did other models. So these were like the start of my study. And then I looked at the work done by other people in the STEM CCS project where they did some dynamic modeling for the standard bookmark. And actually they analyzed the flow of from the reservoir through the chimney through time. So from injection of 200 years of injection, and they force the leak through a point in the chimney of a point of contact between the chimney and the reservoir. And I use from this his dynamic model like snapshots of static snapshots of what happened through time for 5 years injection and the distribution of the CO2 saturations and the height of every advance of CO2 within the chimney. Like, for example, in the 5 years injection scenario, you have 20% saturation at the bottom of the chimney and then 15%. And then I get an inversion scenario that it's very different to the 25 years, where the vertical distribution is a bit different. So you get higher saturation at the bottom of 35%, and then a more diffuse saturation through the chimney. And I think this is very important if we're doing modeling of any geophysical data that we consider um, dynamic modeling. So something I did, because I have gotten this question many times, is that there are limitations, obviously, in detectability with CSEM. So what happened if we were to actually model a smaller structure? So I model a 100-meter chimney structure in diameter, and that this will be still a realistic thing that you will be able to observe in seismic, and that you will be also see in nature and in the literature, like it will be correspondent to any full displacement or a full damage zone where with 100 meters, for example, the vertical displacement according to the literature. And I did the same exercise, so 20% saturation versus 50% saturation. And we already see here that the 20% chimney is starting to be less visible. It is still there. Still there is a response. Sorry. It is still a response, but it's less clear, like that, like than the 50% or the model when you have a bigger chimney. So that's very normal in geophysics. You will have always a trade in your contrast between the property that you're measuring and the size or the resolution of the method. So it's very important to be able to do forward modeling or modeling of any geophysical technique that you're planning to apply for monitoring. So in conclusion, CSEM distinguishes changes in saturation as a leak evolve in the field, and this can be independently detected from seismic but above a specific threshold. Then seismic velocities can detect fluid presence of low saturation. In this specific rock physics modeling that I use will be above 10%. This can change depending on gas distribution and your rock physics properties, porosities, and all of that. So it needs to be adapted to any area where you plan to apply a methodology like this. It means that the utilization of both methods and a multi-physics approach has a lot of value, and that repeat CSEM surveys should be considered as in the MMB strategies that at the moment I don't see it in many of the publications as one of the methodologies that could be used. And I think that's what I have to say for now.